Okay, let's start. A few people, but I think we can try to start. Now I'll share my screen. Tell me, please, do you see my screen?
Yes.
Good. Um, I have a few organization questions. So tell me, please, how many lectures did you see? And did you see some materials about naive bias? And do you know something about it?
This is our first uh, machine learning class.
Okay. Okay. Um, my name is Elisa, and I'll try to teach you something interesting. Today in our program is naive bias and KDE methods. So we will write from scratch naive bias algorithm, and then we will consider kernel density estimator and some techniques for improving our algorithm. Um, Tell me, please, did you work with the Escalon library? And did you have experience Python programming?
Python, yes. sklearn, we didn't specifically, not everyone used it, but we had some questions that used it in the Python course.
Okay, I think in the most cases in our courses we will use Escalon libs, but it's not always optimal and not always effective. But it's simple, and I think it's enough for our course and for educational goals. Um, it's ML libs, and it consists on the different ML algorithm with for classification tasks, for regression tasks, and yep, we will use it. Today we will work with Iris's datasets. I think is the most common dataset in machine learning. I think a few from you familiar with this data set. I see the hand. Um, if you have a question, you can ask me. Okay, I think somebody forget the skip hand. Um, let's try to load the iris dataset. I need to say that in Escalon libs we have some toys dataset, and you can load this dataset for your practice. In website um, Escalon, we can find the different datasets, and when you practice in machine learning algorithm, you can use it because it's really simple for loading in Google Colab, and you for example, take the data set from the Kaggle resources, but if you want to practice, you can use this data. Dataset load iris and iris, sorry, and the libs can provide some information about this data. We can, I think we can draw irises. Mm, 1 second. You have yeah, it's flower, and you have sepal and petal for this flower, and you have this dance and this dance. So petal the same. You have this dance and this. And when we use the data set iris, you have 3 classes and 4 features describes these flowers. You have x1, x2, x3, x4, and this describes this dance on our paint. And when you load dataset and see the describing, you see that it's sepal length, sepal white, petal length, and petal white, and you have 3 classes: iris setosa, iris versicolor, and iris virginica. So you can see some information about this data, mean and max values, mean, SD, class correlations, and yep. So creator of this dataset is Rhys Fisher, and if you are not familiar with this data, I think um, you can read more information about it. But I think today we use this part of information. Okay, you have array, and it's our features. You have 4 features and 3 target. So it's values of sepal length, sepal width, and here you can see array with target values for our data. You can see the feature's name and get 4 names for our columns. And let's try to create the data frame from these values. You have 4 columns with your features, and you have columns target label, characterize target name. You can see the shape of our data set, and yeah, you can be confident that we have 4 features. When you want to solve some machine learning problem, usually you need to explore your data, and we can consider terms is EDA, exploration data analysis. Today we will not see it detailed, but for example, we have matplotlib library and Seaborn library for visualization, and you can see how our data is distribution, and you can notice that our data um, have very division groups, and it means that we can use some classification algorithm for classificate this data and define label of our data. So in this visualization, you can also see target label 0, 0, 1, and 2, and distribution of our 4 features: petal white, petal length, sepal white, sepal length. Yep. And depends each features on other features. Also, you can get such visualization, and we have 4 features, and we now we haven't ability to draw 4 features because we live in a 3-dimensional world, and we want to see some features, for example 3 or 2, and we just choose 0, 1, and 2 features, and then we can draw it on the graphs. Yep, it's also visualization. And we can see feature distribution. What we want to know about distribution. Tell me which the most famous distribution do you know?
Normal.
Oh, yep. It's a good answer. Um, Today we will use exactly normal distribution. I can remind you how it see. You have some function. You have a variance, and you have a mean. And in our world, lots of set of data have normal distribution, but not all. And when we solve some machine learning problem, we need to understand that when we use the normal distribution, it's not always exactly. Our data can have more difficult distribution, and in every tasks, our goal it find this distribution more precisely. So okay, I can draw some graphs. You can the variance, and yep, and you have the mean, your distribution. So I think I'll remind you some things from distribution analysis. You have, um, for example, this distribution, and you need to remember some parameters of this distribution is the mediana parameter, which divide our distribution for two equal part. Moda of this distribution, it's the maximum values of our distribution, and yep, and mean. Well, I think it's here. When you build your distribution of the data, you have graphs for Matplotlib, for example, or Seaborn. And when you have distribution with the unimodal, when you have only one mode in your distribution, you can use normal distribution for describing your data, and it's okay. But sometimes you can have distribution, no, for example, such, and you have two modes in your distribution, and it's not exactly described with helping normal distribution. Let's turn back in our notebooks, and let's try to implement naive Bayes classifier with the normal distribution. And first step is realization Gaussian distribution. You have our formula, and we need to implement with Python just mathematician formula. You have mean, you have STD, and you just get two function for describing this formula. In SciPy libs, you can take the ready normal distribution, and when you solve some machine learning tasks in real life, you use the ready functions, ready distribution, but today we want to write it from scratch. I think it could be interesting, but we can comparing our result with the results from SciPy stats realization, and we get that our distribution and distribution from SciPy stats, it's the same, give the same results. Let's discuss naive Bayes classifier. Tell me why the naive Bayes classifier is naive. I think this information was in lecture.
We didn't have a lecture yet, so we don't have a context yet.
Oh, okay. I think okay. You have the naive Bayes formula, and how we can get this formula. You have conditional probability, for example, PA B. You have event A and you have event B. So when you get the probability A, if you know that event B was happened, you can calculate PAB divide PB. And also you can write the same, but for a B event. And now you can equals the denominator. So this and this. And you see that PAB yep. And now you can get the naive Bayes formula. How we can use this formula for our tasks? You have three classes, our irises, Y1, 2, and 3. And you have vector of features with your sepal length, petal length, and ETD. And with helping this formula, we want to predict our target, our class. Sorry. If we know that vector features is x. And with formula, we can write is like okay, let's discuss why our naive Bayes is naive. When we want to get this probability, so when you have some new data, you want to get label of classes for your vector with some values. And you for it you can calculate this numerator and denominator. Tell me how you can calculate these values if we have three classes. Okay. Yep.
Like first we need the information if they are independent or not, and then we can calculate the prior probability from that.
Okay, let's see. We have three classes, and for each classes, this probability is because you want to choose one target from three classes. This value is constant and is the same for all classes. And when we will found this value, we just skip this constant. So it's just normalize constant. And now our goal is calculate these values. You have some distribution of features, and you want to understand if your features describe some specific label, what is the distribution? And when we considering naive Bayes algorithm, we can consider this vector of features like features independent. What does mean? You have is your this is your features, and you can write like because you assume that this features independent. X1 doesn't depend on X2, and the same things with other features. Okay, we understood what we need to calculate for defining label for new features. Yeah, in our notebook, you can see these operations more detailed, but I think we can go to implementing naive Bayes. Okay, you take unique labels. In our cases, it's 3 labels, and you need to assume which distribution have our data. How I said earlier, we can, in most cases, consider the Gaussian distribution, but not for all cases. And in this part, you write this this part of naive Bayes formula, and we want to calculate distribution of our features if we know that our object from dataset have a label C, K, for example, 1, 2, or 3. More simple part is calculating just you have 3 labels, and you just divide it on len your target massive. And in this part of code, you get naive Bayes classifier. So you can test this and get some values. And in sklearn library, you can call ready naive Bayes classifier and comparing with your implementation. So if you use for testing your realization, we can these metrics on train and on test, and you can compare with sklearn implementation and get almost the same metrics. I think, tell me please, who know about KNN method, K-neighbors classifier? Or you can say if you don't know about it. Okay, I think more detailed we will describe this method next part of our seminars. But now I can tell you that it's approach which I can describe. Tell me who is your friend, and I tell you who are you, and you just see which data is near by you, and know who is your neighbors. You can make the decision who is your. So if we sorry for example, you can gray squared, and near you see red and yellow squared. And if you understand that red squared more than yellow, you define your gray squared like red. If you see that yellow squared more, you define your gray squared like yellow. Okay, it's also algorithm for classification, how you understand, and we can get these metrics. I think we can discuss it more detail in next part our courses. And now, yeah, it's advanced part. What we will consider. You have violin plot visualization. Why it's important? When you build the histogram basic on your data, to be honest, you get not precisely describing of your data. Why? Let's see this image. For example, you have some data points, and these data points distributed such um, have this distribution. And when you build some histogram, you lose some accuracy for your data, because if you see on this data, you can notice that it's very lots of um, values, and when we build a histogram, we assume that this data all on one level. So, for example, we have histogram this, and this bin, our histogram, means only one values. But in these bins, lots of values, to be honest. And it's it's not precise for some tasks. When we want to get more smoothing distribution in our data, I think we can draw, and it will be understandable. But let's try to discuss kernel density estimator. What is it? It's non-parametric methods for estimate distribution your data, and in code this you can see that with helping kernel density estimation, you can get more precisely estimate of your data distribution. So, yep, we assign some probability density to a region around actual observation. Now we can discuss how it works. So let's image that you have some discrete distribution values, and when it's discrete distribution, you can build a histogram, and it will good visualization for your data distribution. But in the most cases, in machine learning, they will work with continuous distribution and continuous random variable. So tell me, please, do you know about PDF and PMF?
Yes.
Okay, good. When we work with discrete variables, you know that you have x1, x2, x3, and you can write numbers of your values countable, and yeah, and you can normalize this. But what we need to do when we have continuous variables? You have, I think, the good analogy is tasks classification and regression. When you solve the classification problem, we consider our targets like countable values. But if we solve the regression problem, our targets is non-countable because it's continuous values. So I think we can write x is our continuous variable. And also this C we need to normalize minus infinity plus infinity. Is 1. So tell me, please, when we see our data is our data frame. Oh, sorry. When we consider some values from sepal-length, sepal-height, and other, we work with discrete values or continuous.
Can you repeat?
When we work with these values, is discrete or is continuous?
Since we were taking the normal distribution, so continuous.
Yep. We assume that it's normal distribution, but to be honest, it's not enough for maximum accuracy in these tasks. And now we will understand why. Earlier we remember it unimodal and multimodal distribution. And if we will see on distribution our features, you can notice that they have not one mode. And when we make assume that is normal distribution, it's not enough true. For what we want to use kernel density estimation? Let's try to understand how it works. Kernel density estimation, I write formula and then we discuss it. Okay. N is number of observations. If we speak about our data set, irises, you have 150 samples, features 1, features 2, 3, and 4. And our data set divide 3 parts, Y1, 2, and 3. So it's approximately 150 samples. So for our for our target, you have 50 values of your features. So n is 50. H is hyperparameter, and we will define it in thickening process. What is K? K is kernel filter, and you use this kernel for defining probability dense in some data point. If we turn back on our sorry, you have a data point is red, and you want to find the distribution which the maximum precisely describe your data. You know that for each target, your features is 50, and then you know mean values, and you know max values for distribution of one features, and you can divide um, your set of values. For example, some part, and you want to describe distribution in every point of your data part. So x e is value from your data set. For example, you know that Virginica irises for x1 have a set of values 1, 2.3, 4.2, and others. And when you calculate this function, you just take these values and yes, and add in this formula. X is your data point, which you considering for defining distribution of estimate dense distribution. And for every point, you need to calculate these values and sum. What is the kernel function? It could be a different function, for example, Gaussian function. So you can see. Mm, okay, it's I want to find which filters, which kernels we can use. The most popular is Gaussian, yes, uniform, triangular, B-weight, G-weight, yep, normal, and others. So these formulas and K could be these functions. And when we calculate these values, you can get the more precisely estimating of estimate density distribution for specific data point. And these methods allows to get more precisely describing of data distribution. And if we understand data distribution, we can in naive Bayes formulas calculate this part and then get these predictions for new data. So we learn distribution features for every target. And then we can use it for new data during the formula. Turn back the notebook. For example, in this code, we take third features and features where targets equal 2. And for these features, build probability density distribution. We can see that it's more smoothing than histogram. And let's try to build Gaussian kernel density estimator. How I said earlier, bandwidth is a hyperparameter, and we can play some, for example, 0.1. And you can see that describing of your distribution more variables. But if we change values of bandwidth 0.3, you can get more smoothing your distribution. If you remember, when we implementing naive Bayes classifier in this part, our notebook, we wrote the function where we can get Gaussian distribution, but we also can use other distribution. And let's try to, in our naive Bayes classifier, use distribution which we got with helping kernel density estimation. So yeah, fit, predict, and get values with the train and test dataset. You can notice that metrics higher than in classical implementation with the Gaussian distribution. And yes, you can build histogram for every features, and then build visualization with helping kernel density estimation. So it's more smoothing and more precisely for your data. You can play with hyperparameters, and also you can change kernels and learn what happens. Okay, I think the most part of the seminar is finished, but I want to show you some things. When we work with naive Bayes classifier, we discussed that you can use normal distribution, but you can try to get more precisely distribution with helping kernel density estimation. But we also have other approaches which can help to um, improve our naive Bayes. And for example, it's Gaussian mixtures. Sorry. Okay, I'll fix the links and send your notebook. But Gaussian mixture approach allow you for your data distribution make assumption that your data from the different normal distribution. So you can image that you have one normal distribution with specific parameters, and you can two normal distribution with some other parameters. And you want to describe your data distribution like mixtures of few normal distribution. And with these methods, you also can improve naive Bayes, because you give abilities consider not only normal distribution unimodal, but for multimodal distribution it's also work, because you use mixture from some normal distribution, and it could be work better. If we speak about naive Bayes classifier, I also want to say that we can use this simple method not only classical machine learning problems, because, for example, for natural language processing, we can use this method for classification letters, spam or not spam. And here I'm not sure that it will be. I don't know why it doesn't work, but I fix it. I sent your notebook with links on Kaggle notebooks, and if you want, you can try to use naive Bayes for natural language problems too, because it's really simple, but you get interesting result. And in big company, it approaches for classification spam or not spam latest still use, because it's really simple, and it's required less computational resources, and sometimes it work really good. And if you use some improving methods, for example, KDE or Gaussian mixture, you can get mm, um, more precisely describing of your distribution, and get better result with naive Bayes classifier. Okay, I think the most information finished. Let's try to discuss some violin plots, why it's important. We said that we want to understand our data better than we can get with helping histograms. And when we use violin plots, you can get estimation density distribution your data, because forms your violin plots, it's density distribution. And I think this visualization could call combination KDE and maybe box plot, because we can see minimal and maximal values, and you also see median of your data, and wide your violin plots is um, sorry um, um, density distribution. We can see some images. I have my favorite image for describing violin plots. You have a box plot and maximum and minimum values. Also, you have median and density plot, where white shows your frequency, your data. It's really better visualization for understanding what happening in your data. Um, okay, I think that's all. I can say some organization questions. I think I create some table with useful materials for you, and after every seminar, you can check this table and maybe read articles for a specific topic, or maybe you can, if you don't understand some moments and you want to get more about it, you can use it. Tell me, do you have questions? Some about informations today.
Where can we see the list of topics that we would be studying for this course?
Sorry, repeat please.
Where can we check the list of topics that we would be studying for this course?
Yes, I think I need to discuss it with organizers of this course, and we will write in chat this information. Do you have any questions about naive bias? Tell me, understand how we define distribution and why it's important.
Yes.
It's really, really good news. Okay, if you haven't questions more, oh sorry, I see question in chat about schedule. I think if it's comfortable for us, we can meet Friday like today. So 6 p.m. I think it's will be okay. Oh, sorry, 6:30, not 6. If it's comfortable for you. Okay, I think we can finish our seminar, and useful materials I'll send you, and this notebook.
Sorry, one more question. We will have the recordings, right? You will send us the recordings.
Yeah.
Okay, thank you very much.